Okay, so in this problem, we're going to show that the curve given by r of t, first component cosine t, sine square root of t, second component sine t, sine square root of t, third component cosine root t, we're going to show that that curve, which is pictured here, kind of spirals around, lies entirely on the unit sphere. So if you were to put the unit sphere in the same picture, you would see that that curve is on the unit sphere the whole time. And how do you prove that? Well, what's really important to realize, you guys, is that r of t is nothing but, and any function you've ever played with is nothing but a set of points, right? And by definition, the graph, which is nothing but a set of points, those points, any point on the graph, satisfies the equation that is the function, in this case, or in this case, the surface for the unit sphere. So to show that a set of points like r of t lies on the unit sphere, all you have to show is that these coordinates, which are x, right, in terms of t, y in terms of t, z in terms of t, satisfy the equation of the surface that we're talking about. And that means automatically, by definition then, that the curve that r of t graphs to be must lie on that surface. So what's the equation of the unit sphere? Yep. And so the idea is I'm just going to plug x in terms of t. I'm going to plug in x in terms of t, the first component, in for x, y in terms of t, the second component, in for y, and z in terms of t in there. And I'm going to verify that I get 1 when I do that. So if I do that, I'll get cosine t sine root t. Okay, I've got to square that guy, right? That's the first component, and I'm squaring that. So that's what I plugged in right there. And then the y component, what am I plugging in? Sine of t and sine of root t. Whoops. So that's the y component, and I'm squaring that. So that's what I plugged in right there. And then the z component, let me scoot over a little bit. The z component, I'm just plugging in cosine of root t in for z. So I get cosine root t, the whole thing squared. And I just need to show that that equals 1, and I'm done. So remember, when you're taking a product and squaring it, the exponent applies to both factors in the product. So I could rewrite this guy as cosine squared t times sine squared of the square root of t plus sine squared t sine squared root t, right? And then just rewriting it using the usual notation, we get plus cosine squared root t. And we're looking for a trig identity here to help us. Yeah, there's something I can factor here. Does everybody see? Let's see, sine squared root t. Does that work? Right there? So just, it only works from the first two terms, right? So factor it out. So sine squared root t. And then just from the first two terms, what's left? Which is good news. And then we still have the plus cosine squared root t. But this guy right here is equal to 1. And so we're left with just sine squared root t plus cosine squared root t. And it's the same identity all over again, right? Cosine squared plus sine squared equals 1. And so in the next step, I'll just say that we get the 1 there, which is what we're after. If you wanted to, you could keep the 1 on the right side, because really we're just verifying that this is true, and then you could just say that. Does that make sense?
Okay, so for the last step, the root t doesn't make a difference?
Doesn't matter. Not a bit. Right. The inputs have to be the same to apply the identity, but they are. And so, you know, I mean, if you look at the identity that we're using, it's cosine squared theta plus sine squared theta. Theta is some angle. We think of it as an angle, even though it doesn't have to be. Equals 1. Okay, theta equals root t. It doesn't matter. It doesn't matter, right?